All right, so I've been working on building a computer. I'm building a VME bus-based computer that I've been planning for a long time now. And I've got the CPU card is all designed and ready to be built. But the intention is to be able to have multiple CPU cards in this same system and have them interact with each other. And in order to do that, I'm going to need some memory. The CPU cards themselves have memory on board, but there needs to be some global memory in the system that all of the CPU cards can access in order to be able to coordinate between them and share work. So I need some kind of memory card. And I started thinking about it, about like, well, I'd like to have a lot of memory, and I'd like to have, wouldn't it be neat if I could use like some old RAM or something like that as the basis for this card? But that kind of quickly devolved into like, well, the form factor I'm dealing with here, which for reference is this. That's the size of the card for a Euro card standard size for 3U that plugs into a backplane. So given this size, a RAM stick will not fit vertically, and a RAM stick will fit horizontally, but I won't have a lot of room. I think it ends up being like to here. So then these transceivers, which I would still need, would be really tight in there. I'd have to put them along here. I would maybe only get four sticks in maximum. And it'd be kind of like 128 megabytes or something that I could fit on there with some old 72-pin RAM. So I moved away from that idea. I started exploring SD-RAM. SD-RAM you can get reasonably cheaply by comparison. I could get 128 megs in 2 to 4 chips instead of, having a whole bunch of space for sims on this board for the size of maybe about twice the size of, or a little less than twice the size of one of these chips. With 4 of them, I could get 128 megs easily. But SD-RAM is a lot more complicated to control. So then that pushes me into an FPGA or something like that to talk to the RAM. And it just, that kind of balloons into a very complicated card. So I kind of figured, well, I'll do that eventually. I'll be able to have a whole bunch of memory in the system by making that card, but it's going to take me about a month or so to do. And I'm kind of I'm taking time off in December, so I would like something sooner. Could I have a stopgap? So, and it would be nice if I designed a card that could be built that didn't have any programmable component. That would make it easier for people to make their own. If anybody wanted to clone this, you wouldn't need some means of programming it to get going. It would be a lot easier to build up such a card. So then my thinking was like, well, okay, I have a lot of static RAM chips, and there are some pseudo static RAM available, which is actually like a DRAM chip, but there's a built-in controller that will allow it to be accessed with a parallel interface as if it were a normal static RAM chip instead of the more complicated DRAM interface. And it'll automatically do the memory refreshing needed for the DRAM, so it looks like a static RAM chip from the outside, it ends up having about the same memory as a static RAM chip anyways. It's about half to a third the price. So instead of paying $12 for 1 megabyte of static RAM, it ends up being about $5 for about the same amount of pseudo static RAM. One of the things with that is that they are like 3.3 volt. So it would be nice if I could make a card that could take either 5 volt or 3.3 volt, parallel interface, standard sort of static RAM chips, and interface them to the VME bus. And one of the things that I then think, of course, about is this whole A40 MD32 cycle, which allows you to multiplex a 32-bit number onto the 16-bit data bus and the 24-bit address bus of a 3U VME card. That ends up getting complicated. It ends up being about like twice as many chips as it would otherwise be. And there's probably still a need to have like a 16-bit 3U card, RAM card, that you can actually use, that isn't too expensive, that can have a decent amount of memory, and that isn't too, too complicated or anything like that. So I ended up thinking, okay, I'll do a regular 3U 16-bit static RAM memory card. So I ended up starting to draw out my design here. Made some notes. I was thinking about, oops, it's a little hard to see, but the zoom on my camera is not as good as just holding it closer. I had previously thought, I'll call my memory card or my memory cards membered, sort of like remembered memory card, something like that. So then I thought, well, okay, if I'm going to have multiple of them, I should call them like each a unique name. So I was looking up birds, and I came across the American woodcock, or sometimes known as the timberdoodle. It's a very small bird, and it has a funny slow walk. So I figured, despite the name, I figured I would go with this as the name for this card. So as you can see, I've taken a few little notes about what might be needed on a card like this. The over here is the signals coming from the VME bus, and then there's some internal signals here. The RAM chips are shown there, and there's not too much complexity to it. When the address strobe signal is active, and the 6 address modifier bits with a particular address code come on to the VME bus, that would essentially activate, it would say, okay, there's a cycle in progress. The address pins would be decoded to figure out if it's an address on this card. It would activate the chip select signals, and then from there we could control the either a transceiver or a latch for the address pins. Those would go into the RAM chip. The data strobe 0 and 1 signals could be used for the upper and lower byte. And then the data coming out of the RAM chip would go through another transceiver onto the data bus. And then in addition to that, we need to drive the DTAC signal, which acknowledges that the data is on the bus. And the cycle can now be completed by whatever requesting controller has initially made the request. So it's not terribly complicated. It's I'll maybe touch on some of the meaning of some of these signals and stuff as we go, but I've left some details about the exact logic and that sort of thing to be determined. But this is a rough idea of what we could build here. So the thinking is make it simple, make it not too expensive, not too complicated, and we'll just avoid the more complicated parts of the VME bus because those aren't really needed right now. So I will, you can see things. So there we are. We're going to make that. All right. So, creating a new project. We'll put it in here. All right, so we'll need some new pages. Guess I can start by putting this in version 1. Export to all sheets. Is that the one? Yeah. All right, gonna need a bus. What else are we going to need? Memory. And I want to switch these around. All right. So I have some existing projects I can copy from. namely the computer card that I've already made, the K30P. So let's see here. We're not going to need this. This is the interrupt stuff. We're just not going to have interrupts on this card. We're not going to have a controller of any kind or anything, so we won't bother about the serial. Interrupt acknowledge in and out can just be wired together. We're not going to need the interrupt acknowledge signal because we're not going to be receiving or generating interrupts. This is actually wrong. I will need to fix this on the other card that I have. We should actually be jumping these together. This is the daisy chain acknowledge on the bus. And we would want a daisy chain, we would want a jumper on that one as well, because we are not going to be doing any bus arbitration on this card. This is just a peripheral card, so no requesting of the bus, no granting of the bus, we just ignore it. We will, however, need to be using the address modifier pins. Don't need this note. We can show the system clock. The buses are labeled VD and VA for VME data, VME address. Everything is preceded by a V to distinguish it from local signals on the bus. Because all of these will be coming from the bus, and then they'll also be on the other side of the transceivers, a different set of pins, different set of wires with different names. Just a recap. I'll show you on this card. This has a 3-row DIN 41612 connector. It's this big connector here. The other board that I made actually has a 4-row. I was doing something a little non-standard with it by putting the pins that would normally appear on the second connector. If you had a card that was a 6U card, it would be longer and it would have 2 of these connectors. And that second connector has the upper 8 bits of the address bus and the upper 16 bits of the data bus, which allow you to have a full 32-bit bus using 2 of these connectors in a 6U card. I wanted to do 3U cards because they're just smaller and cuter. So, and it's more compact. It's not as unwieldy. They're cheaper to make the boards. You know, a smaller board is going to be cheaper. So, so I'm using 3U, 1 connector, 3 rows of connectors, 32 pins in total, and that's these 3 rows here. Row A, row B, and row C. So that's the bus. I'll come back to it. We might need to do some more tweaks here, but pretty much just got a bunch of signals, and it's mostly address and data pins, and then some control signals that coordinate what the actual cycle is and the timing of things. So onto memory, we can also copy this. This is the memory from the K30, but we're not going to need the flash. We won't bother having non-volatile memory on here. I suppose we could, but it's not that important. Now, I use these AS6C 8016 memory chips. So that's these chips here. They are 1 megabyte organized as 16 bits. So it's got 2 separate sets of 16 bits. If we check out the data sheet for them, you can see they've got a lower bit and a lower byte and an upper byte. So you have your addresses that come in, you've got power, and you've got control signals. You've got a chip enable that activates the chip to begin with. The write enable will indicate that whatever is on the bus should be written to memory. The output enable will enable whatever output is being addressed to be put onto the bus. So you would only want one of these to be true at any given time or asserted at any given time. And then you have an LB and a UB, which allows you to selectively turn off one or both of the bytes. So if you were, for example, writing a byte and you only wanted to write one of the bytes but not both of them, you would put the appropriate memory onto whichever, the upper or the lower, and then assert chip enable and write enable. And if you were, for just the 1 byte, you'd do whichever byte you wanted to write. So if you want to write 1 byte, but and not overwrite the adjacent byte in a 16-bit address, the 0 bit of the address is going to address a 16-bit chunk, a 16-bit value. So each address is not byte addressing, it's word addressing. So we'll need to take that into account when when designing this. These are the ones that I've used for my existing computers. I've got a bunch in stock. They're $13 each. They're readily available. They're not too difficult to solder either, because it's quite a convenient package to solder. The pin pitch is quite narrow, but it's reasonable. I haven't actually tried ball grid array. This would be the other kind of option. So you can see this is only $4. It's pseudo-static RAM, but it's the same organization that we have. And it's also a significantly different voltage. So we'll have to factor that in if we would want to even use something, well, specifically more like something like this, which is a RAM chip that will take 3.3 volts. So not 5 volts. These chips, as you can see here, can be 2.7 volts to 5.5 volts. So that means it's 3.3 volts or 5 volts, generally speaking. These are our various options. I thought there was, okay, there's one. So that's 16-bit wide, 3.3 volts max. Ooh, I wonder if you're supposed to even do like or even like 3 volt on the nose. But it's $5.64 a chip, which is not bad. That's a ball grid array. I still have been meaning to do a board that uses a BGA package of some kind, just to get used to like soldering them using my my hot air rework station, but I haven't actually got around to it yet. But I have already spent days and days looking through all of the possible chips that I could buy. And honestly, these are the biggest ones that I can find. As soon as you go above like an 8 megabit chip, it either becomes ridiculously expensive, like 40 to 100 and something dollars for one chip, which is just ridiculous. Or you just run out. There no longer are static RAM chips available. You have to move to a DRAM chip, which of course requires a more complicated control. Or you do a pseudo RAM chip, but the pseudo RAM chips, they're really about the same kind of range. You can maybe get a little more density, but you have to go to a BGA package, and they're absolutely max out at 3.3 volts. So I'm just going to use these AS6C80 16s and go from there. Now, in this case, the ones that I used from the previous, this is the K30P, as I mentioned. I have 2 chips on that, with the data signals for the upper going to one and the data signals for the lower 16 bits going to another. So it's a full 32-bit interface, but again, we're not using that on this this card. We're not going to be doing an A40 cycle. I guess I should explain that quickly as well. Let me see if I have a thing. I'm just pulling up the VME bus spec that I have. So this is the spec for VME bus. This is the VME 64, which contains all of the variations, the superset of all previous VME bus specifications. So these are the we have all sorts of information here. We have like the alignment on the bus for different types of cycles, different the exact, like, which byte is which out of all of the possible bytes in a quad word. So if you are reading a 64-bit value, which itself requires a 6U card, and it also requires multiplexing on the both address and data buses to get a full 64-bit value. If you look here, these are the address modes that the bus can indicate. You can use a 16-bit address cycle where you've only specified the lower 16 bits of the address, which gives you, of course, a maximum of 64,000 address locations, which is not very much. For a 24-bit address, for the A24 cycle, you get 16 megabits. For A32, you need to have the A31 to 24 pins, which are only on the second connector in a 64-bit, a 6U card. That would give you a full 32-bit address, which would be 4 gigabytes of addressable memory. In order to support the ability to have a 32-bit value on a 3U card, they've added the A40 cycle. This is sort of a weird situation where, because you actually have a 24-bit address on the first connector, the first DIN 41612 connector, you can actually get a 40-bit address instead of just a 32-bit address. So you're using the data bus to store your addressing information, and you get these upper bits. It's actually kind of backwards. It's the A31 through A24 is on the upper part of the data bus, and then the lower part has the upper byte for the full 40-bit address mode. So even if you're not using, if you just want to be able to use a 32-bit address, you could still implement the A40 cycle. And then if you want to do a 64-bit address, of course, you do have to multiplex on both the 32-bit address bus and the 32-bit data bus in order to get a 64-bit address, which requires the two connectors, and I'm not even going there. And for the A40 cycle, it would be it kind of changes, like it's kind of its own thing. It's complicated on its own in its own way because it is doing multiplexing on the data bus. So I'm just forgetting about the A40 entirely. A32 only supported on the 6U. Not going to be worrying about that for this card. So it's really just the A16 and the A24 That's the only thing we need to worry about here. The A16, we would essentially assume that the upper byte, instead of it being all zeros, would be all ones, because on the VME bus, all of the signals are pulled high. So if you don't actually drive the signal to anything, it will be a 1. And if we just assume that, then our upper byte for a 16-bit address would just be in the upper part of the A24 space. It would actually be possible to like have completely isolated 16-bit and 24-bit addresses, but we're not going to do that. We're just going to consider them to be the same. If you access a 16-bit address, it's going to be the upper part. The upper part of the space. This also gives us information about what signals correspond to what kind of cycle. If you're reading an even byte or an odd byte as one byte on its own, it will tell you what the how to indicate it. So for us, it's actually pretty easy because we have these two DS1 and DS0 data strobe signals that are broken out on the bus. We do not actually have an address 0-bit. So instead of having the 0-bit, we have DS1 and DS0 to essentially tell us what that 0 single byte address, the least significant bit in the address, will be. If DS1 is low, then it's the odd byte. And if DS1 is low and DS0 is high, then it's the even byte. This is made extra confusing by the fact that we're actually working in big endian. This bus, of course, was made for the 68000, which is a big endian processor. Most modern processors, the x86 and ARM, are little endian, so the byte order is different. Here this shows the byte ordering. So the byte 0, which is your byte at address 0 versus the byte at address 1, or offset 1. So the byte 0 is actually the upper part of the data, and byte 1 is the lower part. So these would be backwards on a little endian system, but because of this, the data bus is oriented like this, where the upper part is actually the even byte, the lower part is the odd byte. Doesn't really make a huge amount of difference for our card here, because if the bytes are swapped, as long as it's consistent throughout the card, then we're good. And the last thing I want to just point out is the address modifier here. We've got 6 pins on the bus, which are used to determine what kind of cycle is being requested. The address strobe signal will go low to tell us that there is an address on the bus and that an address cycle is starting. That also means that the address modifier and the address itself are valid. So once address strobe goes low, we can inspect address modifier and the address itself to figure out if our card is being addressed if we're the one that's supposed to respond. And then we respond and either assert B error to indicate that an error happened and the cycle is no good, or DTAC if everything went fine and we have valid data on the bus, or we have written, if we're being told to write data to memory, we will write it to memory. And that's completed. So the address modifier has a whole bunch of codes. There's some user-defined ones, there's some reserved ones. But there's primarily a series for the A24 and a few for the A16. The A16 was added, I think, after the fact to allow for cheaper, simpler peripheral cards that don't have a lot of address registers or anything that needs to be accessed. Case in point, this card that I have here, if that's viewable, the Zycom XVME 203, I think that is. It's a card that has a timer counter, like two timer counter chips on them, and I believe there's an interrupt controller or something on there as well. It's kind of hard to see the chip, the part numbers on those. This big connector, there's documentation available that shows what these pins are, and some of them are the inputs, and then it will count how many times the input goes from low to high, for example. And then there's some registers on here, and you can essentially read what the count is. So it'd be used for like control systems, for controlling some real world thing. You'd have some external sensor somewhere in a control system that maybe it's like a proximity sensor or something like that, or maybe it's part of a process control, like in a factory or something like that. And it would be, you'd have some kind of sensor that is giving you a value, and then this card could count how many pulses happen, and then you read it. But you basically got like a couple of memory locations on the card that will allow you to read registers in the chips that are on the card, to read the count and stuff like that. And this card is an A16 card. So we could add space for having the A16 address modifier codes. The whole series of them hasn't been added. This is the original spec for the original 24-bit address cycles that you could have, and it's broken out into supervisor and user spaces, which the 68,000 CPU will actually differentiate, and program and data access, which again the 68,000 will differentiate. On the 68,000, these are the function code pins. There's 3 pins that give you a function code. Of course, in this case, there's a lot more. There's a 6-bit code instead of a 3-bit code. So not only do you have the possibility of having these other addressing modes, the A32, for example, the 64-bit A64. The A40 is here, so you've only got a limited number of those. You can see they've added after the fact an A24 lock command, which I believe was like an expansion of the specification. But it looks like the original specification did have the block transfers, which again, a feature of the VME bus, but in this case, not actually something directly supported by the 68,000. It's one of the expanded features of VME beyond just regular 68,000. So we're going to be doing a 16-bit card, so we only need the 16 bits. In the case of the other ones, these pins don't actually exist on this chip. So this is actually incorrect. This should be 15 because we've only got those 15 data bits on this. And the address pins as well. We've only got 0 through 23. But we're going to have multiple chips, so rather than delete those ones, I'm just going to do that. I will revisit the address here. We're probably going to need to shift this. So let's see here. We've got, we're showing 19 address pins, which is 512 kilobytes. So recalling from our datasheet, we've got 19 pins organized in 512 by 16. So that lower, the least significant bit of our address, which we don't have anyways, the LA 0 bit doesn't exist. And we are going to be addressing words and then using the LB and UB signals to select whether we want the upper word or the lower word. So with the other design we had, we were organizing it as two 16-bit chips in a 32-bit pattern. So A2 was addressing the address was addressing a 32-bit chunk instead of a 16-bit chunk. We're going to a 16-bit chunk now, so we actually want the A1 bit here to be our address. So we'll do that for both of these. Get rid of those. For this, I'll just call it, I'll call it LDS and UDS. If you are familiar with the 68,000, don't talk and type at the same time. Okay. If you're familiar with the 68,000, these are the signals used by that, where the data strobe is broken out, the data strobe and the A0 is combined in the chip, and only the UDS and LDS signals come out, which is if A0 is 0 and you're doing a byte access, then only the UDS signal would be low. If it was A0 was a 1 and you're doing a byte access, LDS would be low. If you're doing if A0 is 0 and you're doing a 16-bit access, then both would be low. which is actually the same behavior as our DS1 and DS0 on the VME bus. So we're going to need to do some stuff with them. We're not going to be able to use them directly off the bus. Primarily, this is because we would like to be able to use 3.3 volt chips, or even possibly a different voltage of chips. So we would have to convert those signals coming off of the bus. We're only going to be reading them, so we just need one direction. So we'll convert them from bus voltage down to whatever our board voltage is. And we'll call them LDS and UDS when we do that. We're going to need a read and write. We'll derive them from the possibly from other conditions more than just the one. And then we've got chip selects. So we'll call these CS0 and CS1. So I'm only showing 2 chips at the moment. But the idea would be that we could have more than just 2 chips. How many chips? That's kind of actually a question for this whole. I can get it to focus. The decode there. I show it as a 3 to 8 decoder. To derive the actual chip to select, but we'll see. See what we decide to do. What else can we grab from another board? We can grab some power stuff and a clock. I probably will need an oscillator at some point. It might be possible to get away with not using a clock. The main thing would be for driving the DTAC signal. So again, looking at my little diagram, near the bottom there's DTAC and a counter, which requires a clock. So if we wanted to have a specific delay time for when DTAC will be asserted, then we're going to have a clock. But we might not need that, so I might end up deleting it later. But might as well add it, because it'll save us some time later. IO and transceivers. Okay, we're going to need some transceivers, but I'm actually going to go to my fidget project because we used level converting transceivers in that project. So we might as well grab those ones. Oh, I'm going to need another page. I'll do it like this. I'll do it the proper way. Transceivers, and we want this to be page 4, and transceivers will make page 3. This is kind of it still doesn't do that. I don't know why it doesn't update it, but anyways. Yeah, it's kind of the order that I did for other projects, so that's why I'm copying it. right. Change these while we're at it. 15 and 23. And we'll copy these over here. Whoops. Bus. Oh, I had them down, that's why. I'm like, why are these this orientation? Flip it vertically? Yeah. All right, so this is a an LVC 16245. So this is a bidirectional level converting transceiver. And it allows us to have two voltages. V bus in this case would be our bus voltage, and then our now that I put this in here, I am reminded that in fact these particular transceivers require the one of the voltages be no more than 3.3 volts. So if we use this, we would have to definitely use 3.3 volt logic. If we use one of the other ones, a 74 ABT 1624. This one. So these ones would they all have one voltage, VCC, on both sides. The LVC 16254 is the other one. This one. Yeah, so this is the dual voltage one. I saw it there. I mean, that's saying it right there, 3.3 or 3.6 as being the upper limit of power. But the reason I pulled this up was to see the voltages and what the heck. This is only saying that it is there. That's the one that has dual voltage. I'm going to pull up my other one and copy this. We might end up using this one instead. I think, as it turns out, the pinouts should be okay, such that if we like used this design and had the two separate voltages, if we replace it with this chip, then the voltage pins for the two supplies are just the same supply voltage for this pin, for this chip. And if we powered it with a 5-volt supply, we would be able to use 5-volt memory. So I'm hoping that we'll be able to like design it with this one, but then swap it out for this chip and keep 5 volts. So when we want to use a 5-volt RAM chip, we can use that. Otherwise, we populate the board with a different set of chips for a 3.3 volt. So that's something we should like try and achieve if we can. That's the one stretch goal of this board. We're not going for the A40 cycle. We're not trying to do any 32-bit. We're just a simple 16-bit 3U card. But if we can do 3.3 volt memory as well as 5-volt memory, then we'll be good. Then we have options. We can use a lot of different RAM chips, which would be nice. And now I am like looking for other things that I need to or could copy. What about Big Boy? Here's the 3.3 volt regulator. So if we need to use that, we've got that option. Well, there's a power LED. We could have that. I don't know, maybe. And or like an accessor thing. I'll just put it there for now. Okay. Put it there where you can't see it. Perfect. I should pay more attention to my preview here. All right. Do I need another page? I'll maybe see if I can avoid it. Does that mean I put the logic here? Or here? Or here? Oh, maybe put it here or here. I mean, it is the bus, so, you know, it's kind of like interfacing to a bus thing, so kind of related to the bus stuff. All right. Oh, actually, we need to look at the transceivers first. I'll put this aside. And which is which, and who's a what's it. Now, I have, this is going to be a 24-bit I guess the we if we were doing a 5-volt board, we actually wouldn't need to put the addresses through a transceiver. We do if we want to level convert it, but the address signals, we're not manipulating them, they're just going straight into the RAM chips. So we could actually get away with not having those. But like I say, we want to try and get the 3-volt option available. And that actually means that actually means that we need 24 bits, which is an extra byte, which is another chip, but we're only using 8 bits instead of 16 bits. So do I use an 8-bit transceiver? Yeah. And I thought I actually had the correct voltage converting transceiver on this board, and it looks like I don't. Oh, I do have it. Here we go. Right. Well, we could use that as our upper bits. Get that out of the way, and then copy these things. Oh, these ones, all of these ones, all of them, all of them, all of them. There. E16. Okay, those are not right now. And also, actually, now that I think of it, we need to be LA or something, or VA, right? VA. Well, I think I'm going to take a bit of a break, actually. I'm going to be on later tonight. I'll continue on with this probably in like 2 hours or something. Yeah. I mean, it's a start. You're mostly just copying, mostly just talking, but kind of getting there. I mean, it's not a complicated card, so I should be able to make some good progress. Maybe another couple hours tonight. Hopefully you can join me a bit later if if you are even on here. We'll see how it goes. Thanks for joining. I will see you in 2 to 3 hours. Bye. All right. Let's get back to this. We're designing a memory card, and we would really like it if we could both use the exact same footprints, the exact same board, for 5-volt memory chips and 3.3-volt memory chips. This is a VME bus card, so we've got a VME bus connector on it. It's a 3U single P1 VME bus. So we've only got 16 data lines and 24 address lines. We are not going to support the A40 MD32, which is the 40 addressed pin and multiplexed 32-bit data cycle that the VME bus can support. I am hoping that the CPU card that I've designed, that I'm hoping to build in December, will be able to do a A40 MD32 cycle, but this card isn't going to respond to that. It will only respond to maybe A16, but definitely A24 normal like D8 and D16 cycles. Just thinking here. Yeah. At some point, maybe I will try and maybe even like do this board and then do another board that might try and support the A40, because it'd be really nice if I could. But honestly, like this board is going to have like each 1 meg chip is going to be $13, which means that it's like, you know, if we had 8 chips, that would be nearly $100, wouldn't it? It's a lot. And that would just be 8 megabytes, which, I mean, if it was like that just doesn't seem like a good price. If we can get the $5 chips that are 3.3 volts, that's whatchamacallit, it's one of these ones, isn't it? That was the first one. It's only 4 meg, this one. So like that one. There's that one too. It is a slightly odd voltage. Oh no, that's not. That's a VGA. Anyways, now I'm getting lost in looking at chips again, but this one here is $5. It's a pseudo static RAM. Should be plenty fast enough, but it's 512K. Like it's a 1 mega. It's 8 megabit, which is 1 megabyte. 8 megabit. There it is. With 16 bits. So that's It's not that bad. $40, 8 chips, 8 megabytes. What about 16? 16 megabytes. That'd be the whole AF24 address space, so I guess that would be very useful. Unless we can do the A40. So yeah, it's actually the address space that limits us to. If we're not doing the A40, then there's no point really in going more than eight memory chips. We've got 2 so far, 2 memory chips. They each have a chip select. They each output to the same data bus, which is the local data bus. And then we would have the local data bus. Well, actually, we would. This is incorrect. It's time to start editing things. Duplicate that. This is going to be our data transceiver. Find and replace. ED will become LD. Oh shit! Which side is which? This is the bus side, and that's the data side. So this is gonna be our memory chip side of things. This is going to be the VME bus side of things. No, I don't want to replace those yet. Replace those. Nope, don't do that. These ones. This is going to be LA. Find. No. There you go. There you go. These ones. Not that. And then these are going to be V. What's the, there you, no, that's the wrong one. Is it that? No. Shift F? No. And Control Alt F. Ugh. Control Alt F. Ugh. It's just so weird. Anyways. So A, we are going to match, and it's going to be VA. No. All right, fine. Oh, these ones are VD. That's correct. Skip that one, skip that one. Skip all of those ones. Skip all of those ones. This is just here for no reason. And then these ones are VA. Oh, wait, I need to do those ones. Place. No. Place. Oops. Oh, that's a bus. That's a wire. There's a wire. Come on. Seriously? Seriously. You're gonna force the ortho on me. when I don't. Alright, I'm just gonna move this off. This is like if we want to use the single voltage supply transceivers instead, which I was saying earlier, like I believe the pinout is the same between the AVT and the ALVC. And the ALVC is converting, so it will convert our 5-volt bus voltage into our 3.3 volt memory chip voltage, or less than that if we wanted to do like a lower voltage, we could possibly do that. I believe it's good into like the 1 point something volts. Maybe I'm completely wrong. Should we get lost in this? I mean, this is what I would normally be doing if I wasn't like streaming. I would get lost in all sorts of side tangents. If that's not entertaining, please let me know in chat. I am not seeing things. This is the dual voltage one. Over a 1.5 to 5.5 volt range. Oh, so this one can offer a VCA and VCB can be anywhere in the range. Oh, that's fucking brilliant. Yeah. Because we were looking at the Nexperia one, which was this one, which is also ALVC 16 to 45. This is LVC, not ALVC. Oh, I think I actually have the ALVCs in stock. I should check that and maybe buy some regular LVCs. It says wide supply voltage from 1.2 to 3.6. What? That's not wide. I mean, 1.2 is, but so we could go even lower. Like this one is 1.65, and well, that one's like 1.6, 1.7, or no, 1.8, right? 1.8 is the middle of the range. So that's like 1.8 volts. So that would be fine on an LVC. We wouldn't need an ALVC for that. And I think everything else is like either like nominal 3.3 volt, or you could go like, you know, anywhere from that. So I guess with this one, what would it be like? 2.9 volts. Memory is weird. But I don't see anything that's like below 1.7. Newer memory would possibly be much lower, but I am living in the past. So, what I was saying, I think the pinout of this is actually the same as I won't bother checking, but I think it's the same as this one. So, if I use the LVCs, I'll just change that right now, just in case I forget later. I'll use the regular LVCs. Oh, that's an LVCC. Right, because that's like a different part. That's just an 8-bit one, which I probably got it. I don't have. This is a board that I previously made, and it's got an FPGA and these, and what was supposed to be two there as well, are, I believe, the LVCs. I need light. I don't have a lot of light around here. These are the ALVC Nexperia chips. And then I have a tiny one. Jesus Christ, I can't even read that. My eyes are fucking terrible. Can't even. Holy shit. I'll have to look that up. It looks like it's a Texas Instruments chip, but I mean, it says it's an LVCC, but you never know. The silkscreen and what I actually end up ordering is not always the same thing. Will you focus? Focus, kind of. Not enough light. But this little one down here is the 8-bit one, which I just did because, like, why waste a buffer? I'm kind of need an uneven amount of buffers, but if I do need an extra one, well, now let me think about this. I am actually going to need a level conversion for some single signals. We're gonna need a whole bunch for AM. No, we can do the logic in 5 volts, or like in wide range voltage. So like this, the logic in here, we could use chips that could be 3 volt or 5 volt, or even like populated as different based on the board. And then like all of this logic could be whatever. It's these signals that go into there. Those are the ones that need conversion. And if we only end up with 2, then we could use the the 1 gate and 2 gate parts to do the conversion for those ones, and save us having an extra 1 or 2 transceivers. Or we get like another like 4 or 8 244 chip instead of a 245 chip. If we did that, then yeah, I'm just thinking like if we need like 2 directions for a bunch of random things and we wanted to like throw it onto one of these, then we still actually need the 2 directional ones, and that would be converting some but not all of the pins that we would need. And then we'd still need this extra one anyways, so I'll leave it like this for now. I'll keep using that one because I don't think we need like another one of these big boys. All right. This will be just the same direction. It doesn't need to be the 245, does it? What's the other one? There's like a unidirectional one. why change part numbers when you're already buying a whole bunch of these stupid things and they're already like, they're cheap enough that like the price difference probably isn't huge. So I kind of favor like keeping the number of different parts to a minimum rather than, and also like, you know, part count to a minimum. So that's that. We're gonna need another set for this. 16. X. Okay. Of course, you'd use a wire instead of a bus. All right. Oh, this needs to be. Oh, so that is. I should be. We've got our bus data. Our VME bus, data bus, VME bus, address bus, to our local address bus and our local data bus. And for the memory, we've got our local data bus. So when this is outputting, it'll be onto that bus. Our address bus, our local address bus, is going to always be going into our memory chips. Our address transceivers are always in that direction. Wait a minute. I'm just thinking like, do these always have to be the same? And I mean, it doesn't have to, but it can be, and so we should do that. Data dir. Now, this one, on the other hand, In terms of output enable, if it is outputting onto the bus, we even though we could possibly get away with not actually outputting anything, or like outputting both at the same time, even though technically you aren't supposed to when doing an 8-bit access for one of the 2 bytes, but we'll label them as separate lines. Data OE. LOE? Lower OE? Kind of like loss of echo. But I'll keep with it. UOE. Yeah. I guess. And then a dir OE. Yeah, that's okay. And this one. Do we even need that? Because, like, if we're just using it for our level conversion, we technically don't need these ones. We could use a different part. Should I go to the effort? Should I, at the very least, label it as being a different part, even though I then note it as, like, you could use either part? I don't know. Buffers and transceivers. Get do that. No, we're sucking. How much? It's a few. Two elements of 8. So there's our 16. 2, 2, 4, 5. Okay. Okay. Yeah. Key 2, 4, 5. Six, 4. 6, 6, 4, 6. And it's more expensive. Dual supply, level shifting, but it's got direction and output enable. $16-bit transceiver, no mention of dual supply. It's got one single supply. Accepts voltages up to 5.5. Outputs 3.3. But it's actually in like a bigger package as well, and it also has the direction and output enable, but it also has like clock stuff. So $16,541. Not a dual supply. 5-volt tolerant, but actually outputs at 3.3 volts, which is not really what we want. It does kind of work on the VME bus because in theory the pull-up resistors on the bus are supposed to like pull it up to 2.94, and 2.94 is above the logic level for a logic 1 on the bus. So things should generally work if they are only like pulled up to 3.3 volts. But yeah, it's kind of that difference between like going to some extra effort, having more complexity, having fewer options, but doing it right the way that you should, or doing it the way that probably will be fine, but could potentially cause slightly weird stuff. If it does cause something weird, it's going to be like undetectably weird. Or not undetectable, but just difficult to detect. You're going to have like weird logic values only at some times when you just happen to be out of the tolerances, out of what is allowed. This is just at home though, so it's not like this is industrial equipment. Real industrial equipment. There are a bunch that are like, $1.50. They're all just 245s. Those are the cheapest ones. So yeah, I'm curious. These are Nexperia. That's the LVC one. Is it a matter of like this one doesn't say it's 5-volt tolerant, but not dual supply? So which ones are the dual supply? This doesn't really say on that screen, does it? I know there was a Texas Instruments one that was. That one? Nope. There. That one. Those are all the same package. Pretty sure they're going to be the same pinout. Oh, that's bright. So it was the voltage. Now I've lost it again. Where was it? It was that one. It's 250, 260. These ones, which are 370. So the cost really comes down to whether you have the 5-volt tolerant, also I guess low current. Well, no, these ones do 24. This one does 32 milliamps, which is still kind of low. We're supposed to do like 48 milliamps or something on the VME bus for at least syncing, but I have found it to not be too bad, so we're kind of out of spec anyways, whatever. But there's not really anything that's cheaper or like, you know, for being like simpler. Translators and level shifters. I wouldn't expect there to be. Yeah, so everything's just 245. So I won't get too hung up on it. I'll look up those later. So, getting back to this, let's grab these. I'm going to fill that all up with memory. And then there's the root. I'm going to put some of the logic over here. Although, now that I think about it, maybe I should put some over here. Yeah. All right. What else are we going to need? Oh, that's the wrong direction. They're all the wrong direction. That is it. Going out of our card. We are producing BAir and DTAC, and we are consuming all the rest. Except for data, but you know. The control signals, I mean. Need some music for this. I am gonna listen to some DJ Heartstring. Oh. These are inputs? Yeah. And this is an input, but it's got the no, that's an output, right? These are outputs. That's signal going out. These are signal coming in. These are so we've got our address strobe, our two data strobes, our L word, which we're not using because we are not allowing 32-bit operations. We're not doing a D32 or an MD32 cycle. So we would always just want L word to be low, or sorry, high. If it is low, that means you're a 32-bit word or a long word. If it's high, so if it's low, then you assert BAir. Otherwise, you assert DTAC. Potentially when a little timer expires, but I don't know about the timer. Like what I mean is that it's maybe not needed, but now that I think about it, if you were like actually dealing with a 68,000 or 68030, you could just assert DTAC as soon as the cycle starts, because the CPU will only actually complete the cycle when it can most when it can soonest complete it. So having no wait states, you assert it right away, and then it'll be 2 cycles or whatever later that the cycle actually ends, the bus request. But on the VME bus, it's not the same. Even though the signals are the same as a 68,000 labels the signals, they do actually mean something a little bit different. The order of operations is significant. So the spec actually talks about like the order in which these signals go low is important. And I believe that also applies to DTAC, meaning that DTAC cannot go low until after all of those signals have gone low. There's like a little bunch of ordery things here. There, these ones. So respond, drive DTAC low, receive, read the data, receive these, present the data on the bus, and then drive DTAC low. It might be possible that if you are not entirely sure, so DTAC has to be after DS0 and or DS1 are driven low before DTAC can be driven low. And then DTAC cannot be driven high again until DS, well, in this case, this is a single byte, but like either of the two DSs have to go high, and then you can release DTAC, but not before. Other parts of the spec actually say that like this order of operations is important, and if it doesn't do it in the exact sequence order of this, then it's not conforming to the spec. So that does kind of imply that like we would have a counter for the wait states, but we could possibly get away with no counter as long as we assert DTAC only once one of these two goes low and don't release it until both of these are high. Let's go back to the address modifier stuff. So where was up here? Yeah, here. Okay. So at least for this initial design, we're going to not do the A40, and at the same time, I'm not going to bother implementing lock command. And I won't even bother with this 16-bit, the A16 address space. You would have to use the A24 in order to access this card. A32 requires the second connector, P2, where We're designing this as a 3U card. I'll probably design the like DRAM version of this card with an FPGA and all of that complex bullshit sometime in January if I have time, if I feel like it, depending how the build goes for the CPU card. But I'm gonna do the CPU card. I'm gonna build the CPU card first, and then of course A64 is just that requires both as well, and also is multiplexed. So it looks like the A24 is the only space that we need to worry about. And in every case, the upper 3 bits are always high. The bit 2 is supervisor versus privilege. We are basically ignoring that. They'll basically behave the same. And then high, high, and high, high. High, high, and low, low. Fuck you. But a high, high condition or a low, low condition is a block transfer. And I really should support that, but I'm not going to because it's complicated. Well, okay, so we probably should pick those out. So if bit 1 and 0 are XORed together, and these 3 are high. So I should probably figure out like a better way to do logic. I could just like, you know, write it up in English and decide from there. Why is that formatted weird? What's going on? There we go. Oh, what are we gonna do? We're gonna do an XOR. Quad 2 input XOR. We only need one, don't we? So 0 and 1 XOR together. If that is true, not cancel. Finish. There we go. And do that to signify that it is not connected. We need a do we need an AND or an AND? I do not know. I want the quad input one. Oh, no, it's a 4 input. And what ones do I have? I have the 20s. I have LS20. I have these in stock, which is why I'm using this. Oh, it is like that. Now, since this is a not a multiplex cycle, is that true? I don't know. But definitely, if this is not a multiplex cycle, then AS should be low for the entire duration. So if AS is low and our address modifier matches, and our address matches, which we have to decide on, then we get then we would respond to the cycle. Looking at my diagram, we might as well put in the 3 to 8 decoder. But I'm now kind of like wondering, for well, the address output doesn't really matter so much, but this transceiver, we only want output enable to be active when any of the RAM chips are selected. So I kind of need to make a signal that will be true when any of the RAM selects are being selected. Brains. Brains are the best. The best. We'll get one of these ones. Stick that in there. So what I kept going over in my brain was like, oh my god, these things, we've got 3 of them, but then so it's like, you know, this going into one of these. And if it's low, then it's active and we've got the right thing, and then we do this to the other one, and then we can do something else to the last one, and then we get our 8 signals, and that goes to 8 separate memory chips to select them. But we also need a select that is always true, so then actually we need to put extra gates in here, not actually have this go straight in here, and have some signal that is always true when yeah. So short answer is I'm thinking of adding some more logic. We've got AS will be low for the entire duration. One or both of these will be low for the entire duration. I mean, technically we don't want to enable the transceiver, which is these ones, unless, oh, right, we have 2. Okay. Also, these are the opposite one. The outputs. So we've got 2. And they kind of correspond to those 2. It's actually probably the other way around, but whatever. But that would not be sufficient because we also want this to go into there. And we want OR gates. Gee. Whoops, I didn't mean to do that. First one. Well, I did actually want the first one, but it was a different. All right. All right. One of these will be for that. One of these will be that. I should probably figure out which one's which. We want to keep it consistent here. When during a single byte transfer, when DS1 is low, you're transferring the even byte, and when DS0 is low, you're transferring the odd byte. And L lower is the odd byte. So 1 is the even byte, which is the upper. Just to confirm that. Oh, that doesn't show it. The other one. Where'd it go? This one. Yeah. So single odd byte on D15 to D8. Single. Did I say odd or even? That was the even. This is the odd. It's on the lower byte. Odd lower corresponds to that DS0. DS0. Definitely the low odd byte. I need to like check 5 times. Or I might get it wrong. Oh my god. So if this is 0 and this is 0, this will be 0. Don't care about that. Even trying to find like some nice space for it. I'm wondering if I should like do the thing where I do everything in one giant sprawling schematic. Or whether to put intermediate labels in. I probably should put intermediate labels in. because I actually need to use this signal somewhere. Yeah, CS all, CS any. And then did not want that, I wanted that. There. So if all of this matches and this, oh, wait a minute. Right, I need to think about this a little more. I was thinking of like trying to, so we've got 24 address bits. We've got 16 megabytes for our address space. But and we want to like have maybe a maximum of 8 megabits of SRAM on 8 chips on this board. But that would mean like if we were doing it easily, we would take either all of the lower half of memory or all of the upper half of memory. And that's not all that great. It would be nice if we could put the memory like anywhere. It would have to be contiguous, but we could like have it at, you know, 5 whatever hex instead of it having to be at 0 or at 8. I know there are tips for like comparing, like just a comparator, bitwise comparator, but that wouldn't work because we need not just one small area, but like a range. So it needs to match 5, 6, 7, 8, 9, A, B. Is it even all that practical to have a full 8 megabytes? Maybe I should like make 4 megabytes be the max, 4 chips. And then like require that it be within a certain area. I mean, the whole point of this card is to be static, to not have programmable logic, and to not do a whole bunch of stuff and have a whole bunch of chips. So, in that sense, making it like have to be the upper or the lower. Well, a 2-bit comparator would allow for 4 megabytes. We could have like more and not populate it, because I'm probably not going to put all 8 megabytes on this board, because I might not even use this for long. I might end up like making that DRAM board, do it that way. So I need like a 2-bit comparator. I always forget about XOR gates, and we have a bunch. Oh, actually, we only have all right. We do not have 0. Right, we've only got 1. So that means, oops, that can go. We get an extra bit squeezed in there. And then we've actually only got those two. No, we go to 19. 19. So we've got 3. And the rest of this is not... This is going to be part of the address stuff. So let's take all of this. Well, I am going to so these two we're going to use for comparing. And these two would be used for decoding. Is there a symbol that separate? Guess not. Do I want like dip switches or do I want jumpers? Those dip switches are expensive, so I'll just use jumpers. Pin jumpers, open, not the solder jumpers. Now I'm just like thinking, oh, we need like a high and a low, but then I can use a pull-up resistor or pull-down resistor, or I could just use a 3-pin jumper. Like that. A 2, 23. So that would just like select between whether we want it to be 0 or 1. This output will be 1 if these are not matching, and 0 if they are matching. So if these two are 0, so we use an OR gate. That's our last OR gate on that chip. If these two are 0, then this output is 0. And we would then need to AND it with this. So we need another OR gate. Or actually, what about a 4-input OR gate? There's no 4-input OR gate? Guess not. An AND would not work. We haven't used any inverters yet. There's a single 3-input OR gate. Three-input NOR gate. Maybe I'll just do another one of these. I'll actually maybe put that one there. So this selects which of 4 divisions of 16 we will be occupying, which gives us this signal, which is combined with the address modifier and AS to produce our CSNE. Our CSNE combined with our VD, or our data strip signals, controls our buffer, controls the transceiver here. Data dir is going to be dependent on not write, I was thinking like we need level conversion. We need to level convert that, at least for this signal. Wait a minute, hold on. All right, which is the direction? If it's high, then bus A goes to bus B, which is a read operation. For this bus, it would be the same. It would be a read operation where the local bus is going out. If it is low, then it's a write operation. The data from the bus is going into the chip. So our write pen will be the same as our data direction pin. When this is low, data direction is low. So this is low. So we're going B. B goes on to A. But that also means that this is backwards. Fuck. That goes away. All right. Direction is do that. In the manual, it does actually say A arrow pointing to B because that's like mathematical notation. But in this case, I will do it in the other direction because it is actually like the block is oriented that way. So if it was like backwards, then you have to flip it around in your head, I guess. I don't know. I'm matching the thing. So it's that direction. Arrow is pointing in that direction. It's going in. We only need 3 bits. I'll come back to that later because I might actually need that, right? I mean, that's a good point. We know that this isn't needed. Whoops. No, I just want to delete that. There we go. Okay. So that's our level conversion. We're just going in. If write is high, we're reading. Data direction is high. We're going to be in that direction. So we're reading. It's low. It's B to A, we're going in that direction, so yeah, and that'll go to the memory chip here, and we also have this RD. Oh, we called them UDS. Why don't we just do this? So it is the lower and upper. It's going to be the same symbol, or the same label, like that. And then instead of doing this, that. So that handles that, and then we need I keep getting distracted. read. So we will need to generate the read signal, which is just the inverse of the write signal. We do want them to be mutually exclusive. So I am actually thinking of, can you not do that? Get one of these. I don't know what I'll do with those. I don't know if I'll use them. L word, and these ones are not huge. And address output enable we'll make CSNE. And then we've got this address thing. And I was thinking of throwing that one on there. We would want if address any which is active low. I don't know if I should actually be using VBus or I should make another symbol for but whatever. This one. Doing that. All right. I know I only need a 4 output, a 2 to 4. But I'm thinking, like, what if I put this on and you set this to expect, like, no, that just wouldn't work. Yeah, you just wouldn't have, like, it would not assert. If you put it in an intermediate address, no, it wouldn't at all. It wouldn't at all. No, yeah. So you'd have to have, like, a way of forcing this high or making this a don't care or something like that. I mean, yeah, you'd need like another jumper there. So you either connect it to here or you put the jumper in the other position and then it would be like tied high or low. What do you want it to be? You'd want it to be low. Yeah. Yeah, so the other option, I think I'm gonna just delete that for now. Am I just a dummy? What's the 4-bit one? Oh, there's a 4-bit comparator. What is it even? I thought it was like a 166 or something. I'm misremembering. That's a parallel shift for that. 74 series. $139, right? Okay, 139. Maybe do something interesting with that. Trying to make like just something to be like, this is probably not the one I'm going for. Oh, I like to like put an X through things, but I guess I have ortho. Is that? That. And you can make wiggly lines, but that's like a bus line and not what I want it to actually be, which is just a geometric line. That's just ugly. No, not going to. All right. So these two are backwards. That's the lower one, the upper one. This unit we wouldn't use. We still need to resolve the DTAC stuff. So this would be like a 4 megabyte maximum, 4 chip maximum. I guess I could just put that in there right now. So max 4 chips. where the upper two address lines tell you which of the four megabyte chunks within the 16 megabyte A24 address space, which chunk this card's memory should appear in. That will select this address cell, and if the address is selected, then we're basically going to enable the address buffers there, which will also bring these signals in. Which now I'm kind of like, oh, what about the RAM chip? Or a write cycle. It shows write enable being at the same time as upper and lower byte, which are contingent on DS, which would make sense, and DS. I guess I didn't place that one properly, did I? Because we actually have those. So if we had the two, so this is 1, 2, 3, 4, 5, 6 logic chips. Maybe more than I wanted. I'm sure I can like reduce it somehow. But if I had another one of these, wait, no, that's not what I want. Is it? No, that is what I want, because it's edit, redo, edit, redo. We do actually want an and. We want if this or this, if this is high and this is high, then this should be low. Which, I mean, we've got this one here. Yeah, I don't know. My thinking was like, what if we have to like make this like if either one of these or both of these is true, then and or if those and this is low, then this and maybe I just won't bother. Maybe it doesn't matter. I'll maybe look into it later. I won't get caught up on it now. So I'm curious what symbol I use for this. It is actually the bus. And we do have a VMAN. Look at that. Okay. Hey, no. Address bus and data bus. CS0, CS1, CS2, and CS3. All right. That's our memory chips. That's our transceivers. We still haven't used the clock, but probably will. I need to fix that up with the voltage regulators. I'm getting a little tired though, so I think I'm going to call it. Maybe won't do that. At least not like for this one. That's a lot of spare gates. And we still have DTAC, which would it would be these. So if this is, if both of them are high, then this is high. That's a little different than what I have here. That's not going to work anyways. We need an AND gate, don't we? If it's 0 and 0, then it would be 0. Not what we want. If this is 1, and this is 1, then this is 1. If one or both of these is 0, then this is 0. Well, I'll take the whole thing. I'm kind of like, okay, so anyways, let me just finish this. Finish one thought before starting another. Yeah, I was kind of like, well, okay, well, I've got a 4-input AND gate. I could have these two and have dummy inputs, or I could have like those two, if that and that, but then that's actually not what the condition we want, right? Is we want this or this and this. So we want these, which are already conditional upon that. If those two and these are high, so if these are all 1s, then this is 1, which makes this 0, which makes this 1. So that's high. If either of these are low, then we assert dtac. Now, if we want to do the timer thing, we would just put like an extra flip-flop or an extra counter in there, and then dtac would be the output of that or something. It might be a bit more complicated than that. We might need to like handle, you know, the it going low and it going high. I haven't actually dealt with this. If L word is low, then we should assert BR, which also should like technically prevent dtac from ever being asserted. And then the sender should deassert address strobe. There we go, that one. Address strobe, and then the cycle would end, and then we would have to go through a whole cycle again. I guess I'll move this off here because that's just spare. $86. Wait, oh yeah, that's the source. Two of those. There. Oh. And 14. I guess this actually should be vmem, shouldn't it? And then our logic gates will be all at the right level, and we'll just pick ones that are 5-volt tolerant if we are going to. That just looks ugly. It just looks. So I'll put a to do handle here. So that's left to do. There's probably like some review and stuff. I probably should look into a bit more the write and the read pins and how that works. And see if I can simplify the logic here a little bit. Might be able to. Actually, I'll also put a to do. Do you need a timer? Do you need a timer here? I think this is looking really good though. It's a lot simpler than I was expecting actually. I was expecting it to be simple, but not quite this simple. It's nice. Oh, right. Huh. I already used some A4 versus A. What that is that one? Okay. A4, B, and C. I'll make this unit E and F. And this will be A, this will be B, B of 4. And then I'll have C of 4 and D of 4. But E and F will disappear. And that will be for G. And since I have a clock, I might as well use it for DTAC. Or I can delete it and then I guess it doesn't matter. Yeah. That one. There you go. Main clock is not used. error. Right, because I don't have my libraries configured because I just created a new project for this. I'll copy it from another project. Maybe I should close the project first. Footprints and symbols. Oh, no, I did not want to do that. Paste. Schematic. Oh, no, we don't want footprints. Design rules, run the design rule, check. This needs to be updated. Good, it updates all of them. Can you tell me a number? Different, okay, 11 warnings now. This one also. Update. Looks like they're all just pin not connected. And then some like unused stuff, which is what we expected. We expected things to be unused. All of these pins are not properly labeled as not connected yet. As with these ones, those are not connected. And we're not using system clock. Oh, we're not using system clock. Let's just not use it then. Does this one need to be updated? I guess. Is it a different symbol? What's this error about? And not driven. Oh, that's unrelated. All right. This is looking really nice. It's not like done, but it's like almost done. I need to do like the last 5% of work, which is the 90% of the effort of like thinking through everything and looking at all the data sheets and making sure that everything's right and then making final adjustments. And then I can probably start on layout. So I'll spend some time and just sort of like do my final validation checks on this. And then I don't know if I'll have some time tomorrow, if I'll even feel up for it. Might be later before I design a board. I'd like to get it like the board design should be fairly simple once I have the design locked down. And I'd like to order all of the boards that I'm going to order like December, beginning of December or something. That should give me enough time for the boards to arrive before I have my time off. All right. that's it for today then. Yeah, almost done. Just the last little bit. Clean up and checks and everything. And then I'll get laying out. Thanks for joining, if anybody joined. Don't know if anybody did, but that's about it. Bye.